we introduce NIL, which stands for No Data Imitation Learning, the first imitation learning framework that learns whole-body control policies without curated data. NIL leverages recent video diffusion models to generate reference videos and learns 3D motor skills directly from them. Acquiring physically plausible motor skills across diverse embodiments is critical for robotics and character simulation. Yet, achieving this has always been a major challenge. Traditional reinforcement learning demands meticulously engineered reward functions for every task and body configuration. Imitation learning offers an appealing alternative by learning directly from data. However, it requires high-quality expert demonstrations, which is hard to obtain especially for non-human or unconventional morphologies. What if we could bypass the need for curated data altogether? Our key insight is to leverage video diffusion models to generate expert reference videos on demand and learn 3D motor skills directly from them. These models can produce visually plausible videos of a wide range of motions, from humans to ants. Yet, learning 3D motor skills from 2D videos presents its own challenges. First, extracting 3D information from 2D videos isn't trivial. Second, state-of-the-art imitation learning frameworks rely on adversarial pipelines, which require high-quality 3D data. NIL overcomes these challenges by combining pre-trained video diffusion models with a novel discriminator-free imitation learning framework. Our approach consists of two stages. Stage 1 generates the video. To do so, we render an initial frame that captures the agent's initial pose in the physical simulation. We feed this initial frame with a textual description of the task, such as robot walking, to a pre-trained video diffusion model, and generate a reference video that serves as our expert demonstration. In the second stage, we train the agent to mimic the reference video using our novel discriminator-free imitation learning framework, using a reward based on the video similarity. Our reward function has three key components. First, video similarity compares latent embeddings of the generated video and the rendered agent video to capture spatial and temporal dynamics. Second, image-based similarity computes the intersection over union between video segmentation masks to ensure frame-wise alignment. Third, motion regularization applies penalties to smooth the motion. With this, NIL enables 3D motor skill acquisition from generated 2D videos by integrating video diffusion models with a discriminator-free imitation learning framework. To evaluate our approach, we conduct 3 ablation studies. First, we evaluate how different components of the reward function affect NIL's performance. Video similarity and image similarity help to achieve continuous walking using legs, and regularization improves smoothness. We also compare different video diffusion models to understand which provides the most helpful reference demonstrations. Even imperfect videos can guide NIL to some extent, but more visually plausible videos boost performance of NIL. Kling produces the most visually plausible videos, which results in the highest NIL performance. Finally, we examine how small improvements in video diffusion models improve NIL's performance. Ongoing improvements in generative video models pave the way for learning more challenging tasks in the future. That is, with NIL, robot learning automatically improves as video models improve. To test NIL's versatility, we first evaluate it on locomotion tasks across various robotic embodiments and compare it to data-based lower and upper baselines, which are trained using motion capture data. First, we present results on Unitree H1 and Unitree A1. On certain embodiments, such as the Unitree H1, NIL achieves better performance compared to data-based upper baselines. Second, we show overall results along with learned Talos and Unitree G1 motions. For some embodiments like Talos or the Unitree G1, NIL still outperforms data-based lower baselines despite some unusual gait patterns. Next, we test NIL on whole-body manipulation tasks. In the first task, NIL learns to sit on a chair from a single generated video. Next, NIL learns to balance on a board. Lastly, NIL learns to hang from a high bar. Overall, NIL matches the success rate of the reinforcement learning baseline and produces more natural behaviors in all tasks. In summary, NIL unlocks the potential to learn complex 3D whole-body motor skills without any curated data. As video diffusion models improve, so will the naturalness and complexity of the behaviors NIL can learn. For more details, please check our paper and supplementary materials. Our code will be available. Thanks for watching.